I'm happy to be here today to talk to you all about quantum algorithms, and specifically how we tend to think of quantum algorithms as like very obscure, nebulous black box, but it turns out that we can design them by just considering polynomials. These very simple objects that we're used to from like algebra 1 and algebra 2, we can take these and design quantum algorithms. And I'll walk you through some work that I've done in that direction. So to begin, the underlying puzzle that is at the core of quantum information and quantum computing is that simulating quantum mechanics on a classical computer is a computationally hard problem. And by this, I mean doing things like time evolution, that is simulating the evolution of a wave function under the Schrodinger equation. That is computationally very expensive because the Hamiltonian is typically a very large matrix. And it's not something we can expect to do very easily with classical methods. On the other hand, quantum computing provides a solution, and it says we can just reverse engineer quantum mechanics to do these kinds of simulations. That is, because nature simulates the Schrodinger equation naturally, we can use that ability to perform these computations like time evolution, and perhaps also solve other hard problems. And so that's the name of the game. And in doing that, quantum computing has been shown to provide an advantage for a wide range of problems. And some of these include, of course, Hamiltonian simulation, like I mentioned before, that is simulating the time dynamics, or effectively applying T minus IHT to some initial state. In addition, we can also use quantum computing to search through databases faster. So if we want to find a marked element in some database, we can do that faster quantumly than we can classically. Another very famous example is factoring large integers, that is computing the prime factorization of an integer like this. This is again a problem that classically is exponentially hard, but quantumly we can solve in polynomial time. So we get this exponential speed up in that case. And in any event, what's really remarkable about this is that this tells us that the boundary between hard and easy problems shifts when we go from the classical to the quantum setting. So these problems that we could possibly conceive of solving given enough computational power, that is like these classically easy problems, that's that class there. But that boundary between what we consider to be hard and easy, ones that we can solve and ones that we don't really have much hope for solving, shifts when we go from dealing with bits to dealing with qubits and unitary transformations. However, one of the problems that we kind of faced in developing quantum computing and algorithms and applications is that these algorithms that I showed in the previous slide, like all these three here, they tend to leverage what I'm going to call quantum mechanical thinking. And by this, I mean using properties of quantum mechanics to guide the development of these algorithms. So historically, they've used things like superposition, that is, that quantum states can exist in superposition of a bunch of other states. And this is useful in the search algorithm. They also use things like the complex phase of a wave function. That is, that the wave function has a real and imaginary part, and it also has a complex phase. And this is crucial in the quantum factoring algorithm. And also things like quantum states can be entangled. And this doesn't really have a necessarily direct analog in the classical world, but it is useful in doing things like quantum teleportation. And so this is kind of confusing to our classically accustomed minds, where like we're trained in classical mechanics. What we know and experience in day-to-day life is just classical. And so we don't really have much intuition, so much quantum intuition for developing these algorithms and applications. And as a result, quantum algorithms appear really complicated on the surface. They use all these properties like this to solve problems on quantum computers, but they're not very like intuitive or understandable to us. Quite important. And so what I want to argue today is that this sort of appearance that quantum algorithms have as being very complicated is really just an intimidating disguise. And they're a lot simpler at their core, and I will show you how. And specifically, we can show how these are simpler at the core by kind of taking a step back and recontextualizing a problem that we want to solve into a setting where we can use classical intuition. So one where we can use like classical concepts that we know very well today. And by classical, I mean concepts that are outside of quantum mechanics, so things not just like entanglement and superposition. And specifically what we can do is we'll use very simple mathematical structures, as I alluded to earlier, that is just polynomials to design and interpret quantum algorithms. So just these polynomials that we have a lot of experience with, that have classically been studied for hundreds of years, we can use them and all their well-known properties to design these algorithms. And so specifically, I'm going to use polynomials and their foundational theorems. And these include things like the ability that polynomials have to approximate functions. So smooth functions like cosine and a variety of other functions can be very well approximated by polynomials. And in addition, another classic property of polynomials is the fundamental theorem of algebra, which is that all polynomials factor into products of smaller polynomials. So they factor into a product over all of their roots. And as we'll show you, we can also use that tool to design quantum algorithms. And in any event, the overall punchline is that this classical knowledge that we have and have built up over hundreds of years can be used to guide the development of quantum algorithms and develop applications there. And so in this talk, I want to show you how polynomials guide this development of quantum algorithms. And specifically, I want to show you recipes for constructing general quantum algorithms, as well as parallel quantum algorithms and randomized quantum algorithms, all predicated on these ideas in polynomial theory. And then I'll also discuss a bit about how this suggests some future ideas and future work, and how we can also use polynomials to design new applications of quantum computers and perhaps even some new results in quantum information. So with that said, let's, overall, the punchline is, despite the simplicity of polynomials and the fact that like they're classical and aren't intrinsically grounded in quantum mechanics, they're remarkably effective in designing quantum algorithms, and rather surprisingly so. So with that said, let's jump on in. So as I said before, we are going to use classical intuition on polynomials to design quantum algorithms. And the way we're going to achieve this is through something known as quantum signal processing. And this I will denote by QSP. So it's this abbreviation up top. And in short, what QSP is a framework for designing polynomial transformations of an operator. So by operator, you can think of this as like a large matrix or a Hamiltonian. And what QSP does is allows us to take this large matrix, I've denoted here by A, and map it to a polynomial transformation of that matrix. So for instance, like I have here, it could be a Hamiltonian, and we consider this polynomial here that kind of looks like an exponential function. But for a nearly arbitrary class of polynomials, we can realize these transformations. So I will discuss a bit on how quantum signal processing is achieved, and then in the remainder of the talk, I'll discuss how we can use this to design quantum algorithms for the general case, as well as for the parallel cases and the randomized algorithms.
Bounded order?
What's that?
Bounded order on the polynomials?
Bounded order?
I'm asking.
Oh, like a
So
bounded degree.
Order?
Like the degree of the polynomial?
Yeah.
Yeah, it's a finite degree of polynomial. Yeah. Nothing will be infinite. Okay, so quantum signal processing is realized as a product of rotations. And specifically, it's realized as a product of z rotations interspersed with x rotations, where these z rotations, as I've denoted here, are through some parameterized angle phi. That's what the z rotation looks like. And then on the other hand, the x rotation is through some fixed angle theta. So theta will always be fixed throughout the circuit, whereas the phi is then varied. And so what we'll do is we design a circuit that goes like z rotation, x rotation, z rotation, x rotation. And because these operations don't commute, at the end of the day, what we get is a matrix whose upper left-hand corner, this element up top, is a polynomial in cosine of theta. All right. And the way to think about this is that if we let x be cosine of theta, what we began with is an operator that encoded cosine of theta in its upper left-hand corner. And what we get at the end of the day is an operator that encodes a polynomial of x also in its upper left-hand corner. And in addition, I'm using these dots here to denote just arbitrary entries that are there to retain unitarity, but they don't need to concern us here because we're just going to focus on this upper left-hand corner, or effectively this subsystem of our larger system. So at its core, what we're doing is we're taking this operation here and mapping it to a polynomial of that operation. And then in addition, in this case, I'm just looking at a single qubit. And so x here is just a scalar, just cosine of this angle. And in addition, by tuning the angles through which the phi's rotate, so each one of these operators in blue is a variable rotation, we can generate different classes of polynomials. So if you imagine, we can like change these angles such that we get out a different circuit, and as a result, also a different polynomial. And to hit this home, the easiest polynomials that we can consider are where all of these phase angles are zero. So effectively, we're removing the z rotations from this sequence here. And if we set all these angles equal to zero, the polynomials we got are actually the Chebyshev polynomials. It's like x, so x squared minus 1, or x cubed minus 3x, which are very familiar to us. And in addition, by tuning the angles to other values, we can get out a very large class of polynomials. Okay? And crucially, for any polynomial that satisfies some relatively mild conditions, there is a way in which we can classically determine the corresponding phases to realize that polynomial. And so the workflow is you can design some polynomial that you want to implement, and you can classically determine what phases correspond to that implementation. And you can input those phases into your quantum computer to output this polynomial, to realize it quantum mechanically. Okay? Yeah, go for it.
It's another way of saying what you just said is like, if I have like any polynomial, you can write it as a linear combination of Chebyshev polynomials. Is that,
Not quite. So we're designing this polynomial coherently. So if you were to write it as a linear combination of Chebyshev polynomials, you need to add up all of those sort of incoherently. So it'd be like one unitary plus another unitary plus another unitary. But instead, what we're doing in quantum signal processing is realizing that sum of polynomials, the sum of Chebyshev polynomials, coherently all through this one unitary output. It turns out, not quite in the case of Chebyshev polynomials, but if you can realize just monomials, just like x squared, x cubed, and you want to add those up to construct a polynomial, that's actually a lot less efficient than realizing it coherently through quantum signal processing. So it pays to realize the polynomial directly rather than as a sum of a bunch of individual terms.
You're going to do an example because at this point I'm kind of lost.
An example.
And,
of the
and I'm
polynomial.
ignorant, so don't worry about it.
Okay.
I'm lost. It's okay.
Yeah. So I mean, does this example make sense?
No. We can start at the top. So unitary rotations, yay, good with that. That p cosine theta bothers me because I got phi's in there too. So
P depends on the phi's.
Okay, p depends.
Yeah.
All right.
P is not one individual polynomial, but if we change these angles, we can generate a bunch of different polynomials.
Right.
Think of P as a parameterized polynomial.
Now I'm much better. I'm
That
actually
makes sense?
much
Okay.
better now. So then they're going to give us an actual example of tuning.
Yeah, I will provide those. I'll show you how we can
Thank you.
use
Never
this.
mind.
Yeah.
So I didn't say anything.
Yeah.
So-
Yeah, go for it.
So, like SU2 is only so big. And so like, I shouldn't need an arbitrary number of rotations, right? I should only need like 3.
To realize an arbitrary polynomial.
Yeah. Or
Well, if you look at the circuit that we have here, and I'll discuss this on the next slide, if we only have 3 rotations, we can only generate a polynomial of degree 3. Because it's only a product of 3 operators. Right, so if you wanted to generate a degree 4 or 5 polynomial, you would need more than just 3 rotations.
okay, I guess I'm just thinking about like, you could rotate your qubit to anywhere on the Bloch sphere with just 3, right?
Yes, if your goal is to map from just one state to another, that is the case. But as we'll show in the next slide, we generalize this from 1 qubit to larger operators.
Okay, yeah.
And in that case, you really do
Yes.
need like a larger transformation. Are there any more questions?
Yeah, the fact that you set this up in this way with the theta fixed makes the polynomials, the Chebyshev polynomials. Are you ever going to want to play with the phi's and use ultraspherical polynomials? And so you basically the next generalization
I don't
beyond
know much
Chebyshev.
about ultraspherical polynomials.
Well,
but
the order is Chebyshev polynomials, then Legendre
yeah.
polynomials is the 3-dimensional equivalent, and then ultraspherical, any dimensional.
Oh,
Right.
okay.
So this is just this is 2D. This is the sort of the
Yeah.
2D version of that.
Okay.
Taking advantage of the fact that a single angle and cosine, of any power can be written as a polynomial of cosine.
Mhm.
For Chebyshev polynomials. There's an analog thing for rotation on a free sphere. and a
Yeah.
two-sphere.
So maybe it'd be the case that like a multivariate generalization of this would correspond to that.
Yeah.
But we're just going to focus on polynomials in one variable here. Yeah, I'm happy to chat about that later.
I think there are
And then
some
just
papers on
to
that.
round up the stupid
Yeah.
questions. So that p, if I were being a real rotational pedant, that would be p phi d phi, whatever the phi's here there.
Yeah,
They have
exactly.
all phi's in there.
Yeah.
Okay.
So it depends on all of these angles. Even if you change just the first one, it'll change the polynomial.
No, good.
So I'm stating without proof that you can tune these angles to generate a very large class of polynomials. You'll have to believe me on that. The proof is quite long, but I can provide you 2 reference that does this. Does that make sense? Okay. So this is just for 1 qubit. We're just looking at 2 by 2 matrices. But rather miraculously, this generalizes to larger operators. So if we consider A to be an arbitrary n qubit operation, just on some arbitrarily large system, we can design a sequence that allows us to be mapped from this operator here on the left that block encodes our matrix A. So it kind of looks like our X rotation that block encoded cosine of theta. And we can map that to a unitary that now block encodes polynomial of n. Okay? So believe me on this, where this polynomial acts on the eigenvalues of this. And the construction is very analogous. We're going to take our operator, this block encoding of A, and intersperse it with some operators that act like a Z rotation in this larger dimensional space. The Z rotations can be constructed. There's a way to do this. And again, by tuning these angles, we can generate a large class of polynomials out here. Where again, this polynomial depends on those angles that we choose, but we can realize a sufficiently large class such that we can use this tool to develop polynomials.
That's a Cayley-Hamilton sort of thing that you're gonna do there. No?
What kind of Cayley-Hamilton?
Well, it's a polynomial, so it's assuming that its P of A is a polynomial in A, the matrix.
Correct.
So, it's easy to calculate those powers, no
Um,
matter how high they go. Because of the size of the matrix will determine the,
computation. Yeah. So one of the nice things about doing this quantumly is that if we wanted to generate like a polynomial transformation of a matrix, we would need to linear algebra in that vector space. And that could be a large vector space. Whereas if we have that quantum mechanically, we're effectively applying this transformation to the eigenvalues agnostic to the eigenvalues themselves. And not exactly doing the linear algebra because the quantum computer is doing that calculation under the way. Yeah, thanks. Another point that I want to mention is that the cost of realizing a degree D polynomial, to go back to the question we had earlier, is D queries to the operator A. So if we want P to be a degree D polynomial of degree 10, then we need D calls to operator A as we have in the sequence. And that makes sense because if we want to generate, a power of matrix of power D, we need to call it at least D times in this sequence. Okay. So to summarize, there are two key takeaways from quantum signal processing that I want to emphasize. The first one is that if we're given a block encoding of an operator A, we can transform it to a nearly arbitrary polynomial. So effectively, we're going from operator to polynomial of that operator. Where the only constraint it really needs to satisfy is that the magnitude needs to be less than 1, because otherwise this operation wouldn't be unitary. But you can imagine some rescaling or whatever target polynomial you have in mind to meet this condition. So it's a very large class of polynomials that can be generated. And then the second key point is that the cost of realizing a degree D polynomial is D calls to M. Okay? And we will use these two tools to design quantum algorithms. All right, before I go into how we design algorithms, are there any remaining questions about this instruction? Yeah.
So when I think about the block encodings and the difficulty, the complexity of the block encodings, does that have to do with the spectrum, or does that have to do with the density of components, or some combination of both?
I wouldn't say it depends intrinsically on the spectrum. It depends on more so, like you said, the density of the components. So like if A is large sum of a bunch of unitary operators, that would be more expensive than if A is like just one single like C map.
And so you're always thinking of the complexity in terms of how I can rewrite it in terms of unitaries.
Yes, because it needs to be encoded in a larger unit.
Yep.
So like there will be some cost associated to doing that encoding, and that's the cost here. So the cost will scale as the degree of your polynomial. So you can think of that as doing like D calls to whatever unitary encoding you have. So it takes you, I don't know, 10 Toffoli gates to encode your operator. Then your total cost will be 10 times D. Right? It'll be O of D at the end of the day. Is that all clear? Yeah.
Yeah, sorry. That's when you're taking absolute value of P of A, that's an operator norm, or which norm is it?
Yeah, so really it actually is an operator norm. I'm being heuristic here, but just imagine that it's an operator norm over all of the eigenvalues of A under the assumption that eigenvalues remain bounded within -1 to 1. So there's an additional caveat because this also needs to be encoded here. And so really A needs to have bounded eigenvalues, and the output, that is the polynomial of A, also needs to have bounded eigenvalues. But that can all be met by just rescaling the input operator and rescaling your polynomial of interest. All right. Yeah, go for it.
Oh, you said you get like a large class of polynomials. Is it like kind of those with this bounded operator norm?
Yeah, so it really corresponds to bounded operator norm, but if you think of it, if you consider the case where all of the eigenvalues of A are within the range of -1 to 1, this just means that the polynomial also has to be within the range -1 to 1 in that range. So as long as you satisfy that, you can realize that polynomial.
But I mean, if your Hilbert space is bounded, like none of this matters, right?
Yeah, precisely. Yeah. I'm not considering like infinities just yet. All right, so we're going to take this tool and show you can design quantum algorithms with it, and it's very simple and intuitive. All right, so first we're going to cover general quantum algorithms based on quantum signal processing. Oh yeah, go for it.
Thank you.
So with quantum signal processing, we can design algorithms by just thinking of polynomials. And the key is to, again, take a step back and think of a problem in terms of just classical intuition. And specifically what we can do is we can reduce a problem to classical function approximation, which is historically very well understood. Take, for instance, this textbook from the 60s. Like, we know how to approximate functions with polynomials. And we can take all of that knowledge and adapt it to polynomial algorithms. And the specific recipe is to first take whatever problem you're considering and recast it as a function evaluation problem. So something like Hamiltonian simulation or something you want to do with a quantum computer, recast it as evaluating a function f of a. And I'll provide examples for how this works on the next couple slides, but just bear with me for a second. Then the next step is to call to our knowledge on classical polynomial approximation and approximate this function as a polynomial. That we know how to do classically, like we have these good approximations, and we can solve that analytically. And then as our last step, we can realize this polynomial with quantum signal processing, and then implement that on a quantum computer and effectively solve our problem. And that provides a very direct prescription for developing quantum algorithms. And to really hit this home, let's consider an example, which will be Hamiltonian simulation, in which we want to simulate the time dynamics of a system, or equivalently prepare the state that is e to the minus iht times an initial state. And if we follow our recipe, the first step is to realize that we can recast this problem as a function evaluation problem, where a function acts on the Hamiltonian. That is, the Hamiltonian is now the operator. And the function we want to realize is the complex exponential, so e to the minus iht. And then our step 2 is to approximate e to the minus iht as a polynomial. And this can be done because e to the minus iht breaks into cosine and sine, both of which can be approximated by, say, taking the Chebyshev expansion or truncating the Taylor series. It can be approximated very well by doing so. And specifically, if we use some results in polynomial approximation theory, it can be shown that if we want to approximate this polynomial to some error epsilon, the required degree of the polynomial we need scales as O of t plus log 1 over epsilon. So if we want to simulate for a larger time, we need a larger degree polynomial. And if we want a smaller error, we also need a larger degree polynomial. The error scales as log 1 over epsilon versus the linear scaling time. But in any event, this tells us that because the degree of the polynomial we want to realize corresponds to the cost of quantum signal processing, the overall cost of doing Hamiltonian simulation with QSP also scales as O of t plus log 1 over epsilon. All right? Is that part clear? So it's like a very direct and intuitive way to design these algorithms by just thinking about what do we want to realize and how can we do that with a polynomial, and how can we use polynomial intuition or like the classical knowledge that we have to determine the cost of doing that.
What is t here?
What is t?
Yeah.
It's the total simulation time. So if you want to simulate a system for however many seconds, that's the time you specify. Okay. As another example, we can consider thermal state preparation, in which case we want to prepare the thermal state e to the minus beta h divided by the partition function. And if we follow the prescription that we had before, we can recast this as realizing a function that is e to the minus beta h, that is the decaying exponential acting on the Hamiltonian. And then with this realization, we can do what we did before and approximate this as a polynomial to some total error epsilon. And as it turns out, we can actually use the same sort of expansion that we had in the previous slide, which is this Jacobi-Anger expansion for the exponential function. It dates back to the 1840s. And what we find is that the degree required to approximate e to the minus beta h scales as square root of beta times log 1 over epsilon. So if we want to approach a, say, a lower temperature that is a larger beta, then we need a larger degree because beta grows. And similarly, if we want a smaller error, we also need a larger degree because that means epsilon shrinks and log 1 over epsilon grows. And in any event, this tells us that the cost of the quantum signal processing algorithm to realize this transformation and hence prepare the thermal state also scales as square root of beta times log 1 over epsilon. All right. And again, this is all predicated on classical polynomial results, which date back to the 1800s, which is pretty awesome. Yeah, go for it.
Is the number of particles encoded in beta or epsilon?
The number of particles would be encoded in the Hamiltonian. Yeah, I see. Beta and epsilon, you can choose like what temperature you want to simulate a system at and to what level of precision you want. So that can be tuned to your desire.
So the cost doesn't scale with the number of particles, is that correct?
So there will still be a cost associated with the number of particles, but that will correspond to how you block and code the Hamiltonian. So you can think of that as being like a multiplicative prefactor out front of here. It might depend like linearly on the system size, or quadratically or something. It depends on what your Hamiltonian is and how you realize that blocking code.
Are you going to say a little bit more about that block encoding, like how you actually do it? Or...
I hadn't planned to talk about it in here. I'm happy to talk about it afterwards.
Okay, yeah.
But there are ways in which, again, if your Hamiltonian is like a linear combination of unitaries, you can construct a similar block encoding that is unitary as like a linear combination of those individual terms.
Okay, gotcha. Yeah, but it sounds like something that it's not like a cost that we should be all worried about, maybe.
It is something you should be kind of worried about in practice, but on the theoretical side, we just assume that it can be done. Like,
Yes.
we assume that access to that as an oracle,
Yes.
and then we work
okay.
with that in design algorithms. So
Okay.
I'm working on like the designing algorithms part here. But I'm more than happy to talk about how you would actually realize that the block encoding.
I see. Thank you.
So as it turns out, this methodology applies to the elementary quantum algorithms, that is Hamiltonian simulation, searching databases, and factoring integers. And it also applies to problems beyond this, including thermal state preparation and estimating entanglement entropy, and even solving linear systems of equations. And so by virtue of this, quantum signal processing unifies quantum algorithms in that the previous constructions for all of these problems, they're shared very little in common, but now they're all tied together through the framework of quantum signal processing. So it is in this sense that it unifies all these together. And it does so again by using just classical polynomial approximations, which date back like the 18 and 1900s, and we just very straightforwardly apply them to quantum algorithms. Okay, so with the construction of general algorithms, I would think.
Here's some stupid question. So, for example, if you're doing dynamical evolution or thermal evolution, can you see changes in the the way you approximate the polynomials if you're having different complexities in, let's say, the phases that you're sampling? It's a weird question. In the sense like you can always approximate, let's say, negative beta h, but let's say you start with a wave function in one phase and you're going to a wave function in a different phase. You just never see that in your polynomial construction, or would you see something?
Do you mean like if you're simulating time evolution?
Time evolution or thermal evolution, either one.
So like you simulate time evolution of a state and it goes from one state of matter to another?
Right.
Not that I know of. I think one thing that could be said is that if you want to really see that that change from one phase to another, you would need a sufficiently small epsilon, that is a sufficiently small accuracy, such that you can actually really see that change in the state of matter. So I think by that sense, that would be encoded in the epsilon parameter, but you wouldn't explicitly encode anything about the initial state in the polynomial itself, because the polynomial is agnostic to what you applied.
We're stopped. So I understand that you can, if you make these choices of like x and like generalized x and z gates, you can write it in a polynomial form. But I guess I'm trying to understand how this is different from if I just give you some set of gates that I say, okay, now I can generate good approximations to any unitary, right? It doesn't necessarily have to be a polynomial form. It seems like you could run the same game you're playing, except throw away polynomial approximation, just do unitary approximation for the subspace. Is there any particular reason why polynomials are nice here versus just like generating approximation for a generic unitary?
I think it's generally a very hard problem to design an approximation to a unitary just given some set of unitaries. Like the Solvay-Kitaev theorem says this can be done, but constructing a precise way to do that is quite hard.
I see.
And what's nice about quantum signal processing is it gives us a way to do that, and one that's also very intuitive to what we know in terms of like classical polynomial theory.
Sure, I see.
And so like, yeah, if you're given some other basis state of unitaries, some basis of unitaries, you could conceivably construct similar approximations, but there's not a clear prescription for doing that. Whereas here we have clear instructions for how to actually do that.
I see.
And that's sort of like the remarkable part about quantum signal. It gives us this prescription, and it does so in language of polynomials, which we know very well. All right, so next I want to talk about parallel algorithms. So as I've shown you before, quantum signal processing is a very powerful tool for designing quantum algorithms. And if we want to develop this further, we can take inspiration from classical computing concepts. And an important concept in classical computing is parallelization. That is when we take a problem and split up into a bunch of different subproblems and solve those concurrently, then aggregate together those results to solve some initial problem of interest. And what's nice about this is that it enables a trade-off between whatever spatial and temporal resources we have, that we can parallelize a computation over many clusters or many cores on our computers. And it's also very heavily used today in my laptop and in my phone. And so the natural question that we have is, how about we parallelize quantum processing? And is there an intuitive way to do so? And if we think about what it really means to parallelize quantum signal processing, what we want to do is we want to take one of these computations and split it up into a bunch of smaller QSP computations. And so if we take a step back and think in terms of polynomials, what we're doing is, if we do QSP, we generate some polynomial. And if we want to split up that polynomial into smaller polynomials, we can do so by factoring that polynomial, right? So we have some target polynomial P that we want to realize. You could imagine breaking it up into, say, K polynomials, where the degree of each of those constituent polynomials is reduced by a factor of K. So, for instance, if we were considering a degree 4 polynomial, like x to the 4 minus 1, you can imagine breaking that up into 2 polynomials and then running those polynomials separately on 2 quantum computers. And crucially, each one of those calls to these 2 degree 2 polynomials would be cheaper than implementing, one single degree 4 polynomial. And then in addition, this is all based on the fundamental theorem for algebra, which again was proven back in like the 1800s. And it guarantees that we can always factor some polynomial into something like this. So this decomposition always exists. And I will also remark that there are classical methods for factoring polynomials over, say, real numbers or real coefficients, such that if we're given some target polynomial and we want to factor into like 3 or 4 smaller polynomials, we can do that classically. So that part can be done. And so what we did with this idea is we developed something known as parallel QSP for parallelizing quantum signal processing computations. And rather naturally, the recipe is to first take your polynomial, factorize it into K factor polynomials, and then implement these factor polynomials on circuits of shorter depth. So if we were to just directly implement this polynomial as an ordinary quantum signal processing sequence, the depth would scale as the degree of that polynomial. Like I mentioned earlier, we have like x rotation, z rotation, x rotation. We need d of those, and so that would be equivalent to a circuit of depth d. And then on the other hand, in parallel QSP, we can implement each of these factor polynomials, uj, in parallel, where each of these factor polynomials has degree d over k. And in addition, this operation here is known as a swap operation. I'll briefly show you what it is, but what it allows us to do is to multiply together these factor polynomials to reconstruct the target polynomial itself. So very briefly, what this does is it takes, say, some states that are arranged in parallel as tensor products. And if you take the trace of this multiplies them together. So this is just an identity on quantum systems. But what's nice about this is that it allows us to multiply these polynomials together to reconstruct this larger polynomial, where we've decomposed it into these smaller polynomials. Is that part intuitively clear?
It's deep. So I guess the question is, how far can you go? And I don't, I didn't know about Gauss's theorem.
The fundamental theorem.
So how far down can you go? I mean, what are the smallest order factors that you can generate?
Yeah, so there is a cost associated with doing this decomposition. So you wouldn't want to do it, say, to arbitrarily many systems. There's a cost that scales, in some cases, exponentially with how many splits you do. Like if you wanted to use parallel QSP to estimate some observable or some quantity, you need to run your circuit many times and draw samples. And so there is a cost associated with it, parallelizing this over 2 systems versus 4 systems versus 6 systems that increases the number of systems.
I'm just being stupid. This is a pole, in my parlance, this is a pole sort of problem. You're looking at the roots of the polynomial and you factor it that way.
Yeah.
Sorry.
Yeah.
Never mind.
Yeah, so what you do is you can consider like the companion matrix method for computing the roots of polynomials, and that can be done classically in both BIQS time. So what you do is you design your target polynomial, and then you take the coefficients of the polynomial and you put them into this classical method to determine the roots and hence the factor polynomials. And then you implement those factor polynomials on the quantum computer. So there's like a classical pre-computation step, but it's guaranteed to be efficient, and it's something we know we can do in like Python and MATLAB.
I guess the part that's perhaps not efficient is the swap. It is
Yeah.
how entangled the quantum computer has to be for the swap to actually even make that work. I don't know if you actually care or you're just going to assume that it
Yeah.
actually
So
works.
a naive implementation of the swap test over K systems achieves a depth that scales as O over K. So that would cause your depth to be O d over k plus k. However, a couple of years ago, there was someone who developed a new method for doing this in constant depth. So the swap operation can be done in constant depth. If you want to learn more about it, actually talk with Braden, who's the expert. He's working on a project on this, but that part can be done in constant depth. And so in practice, more of the cost will be encoded in actually realizing the polynomials with functional processing.
So what prevents you from doing doing quantum problems as path integrals, right? So you can always take, e to the negative beta h or e to the I h t and break them up very easily into separate smaller time or smaller beta pieces and do this.
Do something like this.
So, but then you have to swap lots and lots of pieces. Is that computationally inefficient or efficient?
Yeah, so you need to swap a lot of things. And there's a crucial point that I don't have on this slide, but it's in the appendix slide, and which says that there's an additional cost associated with how many systems you do parallelize over. So this allows you to reduce the circuit depth, which is really great if your system suffers from, say, short coherence times in your qubits. But you need to repeat your operation more times, such that you can actually realize the quantity that you want to extract at the end of the day. So basically, rather than, say, running a very deep circuit, we run many smaller circuits. And in practice, if we're limited in our hardware capabilities, it might be easier to run those many smaller circuits than one very deep circuit.
So in particular if you want to do the time evolution of a quantum problem and break it up into smaller time pieces.
There's a cost associated with it.
Right, and is that cost prohibitive?
It is prohibitive in that case. And so what we show in our work is actually that this parallel quantum pseudo processing framework applies very nicely to estimating quantum many-body properties. So if you want to estimate something like the entanglement entropy of a state, you can do so with quantum signal processing, with this parallel quantum signal processing method, and split up that computation over many quantum cores.
And have you, I'm riffing on what Brenda said, have you framed this in terms of, so there's a cost of swapping and there's a cost of factorization. So, I do optimization. So have you thought about it in terms of those, some sort of cost function?
I have not. So the cost of factorization is classical and that part is efficient. The cost of swap is quantum, but it can be reduced to constant depth. So there's a construction out there that does the swap operation very efficiently.
So but I guess what I'm asking is, so we know that for a kth order polynomial, we can drop it down to first order polynomials, product of first order polynomials, k of them. What if I did, let's say k is even, I did square polynomials and k over 2 of them, which one is better? Cost perspective.
If you do what versus what? So
let's say, so we take this k order polynomial where k is even, and we bust it out into, one constant plus x, constant plus x, and so forth. So there's k of those, and you got to do k swaps, right? What if I did a plus bx plus cx, and then something plus that? So now I have only k over 2 of those things, and now I only have to do k over 2 swaps?
Yeah, so you do 2 swaps in that case. If you split your polynomial into, if you have the degree of a polynomial.
No, if I now I use square elements instead of linear.
Okay,
pieces, I do square.
The square one would likely be more efficient. And the reason for that is that the number of splits you do causes an increase in the number of measurements you need to take at the end of the day. So you can do the parallelization, but it increases the number of measurements by a factor that depends on the polynomial, which is again explained in our work. But there is a cost associated with doing this many splittings. And so in practice, you can do some modest number of splittings.
So I don't mean to, because I don't want to take too much time, but I'm looking to do an optimization that maybe hasn't been done, but that somebody might want to do.
Yeah.
Okay.
I have this cost explained in the appendix slide. I will happily go over it at the end of the day. It's just like it's a very formal theorem, and I want to explain the heuristics and what's going on. So we can use this for estimating quantum many-body properties. And what's really nice about this is it allows us to use whatever or make maximal available use of whatever temporal and spatial resources we have in our quantum computer. So you can imagine if we have a situation in which we have many qubits, but they have short coherence times, it might be better to tailor our algorithms to something like parallel quantum signal processing, which would be nicely suited to that situation, as opposed to ordinary quantum signal processing, which would require longer coherence time, but on a smaller number of qubits. And so by virtue of this and this flexibility, you can imagine applying it to estimate quantum many-body properties with many noisy qubits, which is the area that we're approaching in quantum computing. Okay. With that said, I will now discuss the last component, which is randomized quantum algorithms. And this one I think is really cool. So continuing to take themes from classical computing, another theme is randomization, which is the backbone of, say, Monte Carlo algorithms, stochastic gradient descent, and a lot of classical algorithms that we think about every day. And so you might ask, how can we use randomization in the context of quantum algorithms and quantum signal processing? And the key idea is, if we think about randomization as applied to quantum signal processing, that's equivalent to saying, how can we apply a random series of polynomials? So you can imagine realizing a bunch of different polynomials and averaging over all of them. And I'll show you that this is actually advantageous in a wide variety of settings. And so along these lines, something we did is develop stochastic quantum signal processing as a general framework for designing randomized quantum algorithms. And as I will show you, we're able to reduce the cost of our algorithm, that is overall time or gate count, by a factor of 1/2 by just introducing randomization. So if your deterministic algorithm would take like an hour to run, the randomized one takes, say, 30 minutes. So it's a constant factor reduction. And in more detail, how this looks is, in ordinary quantum signal processing, we apply one deterministic polynomial. And the cost of realizing that is the degree of that polynomial. And the circuit looks like this. Take some state, you apply that polynomial. On the other hand, in stochastic quantum signal processing, we apply some polynomial pj, which I will specify later, with some probability lowercase pj. And if you choose these polynomials and probabilities correctly, you can reduce the cost in realizing this algorithm by a factor of 1/2. So it's now 1/2 times the degree. And the sort of overall algorithm or circuit looks like this. We're taking a computation value over a bunch of different polynomials that are applied to some input state.
When you say the 1/2, is that robust to the error bars that you get? So for a given accuracy, I would still get the 1/2 regardless of the accuracy?
If you're given accuracy.
So you're taking an expectation value, so you're going to have error bars, and so then does the 1/2 change with the error bars that you have?
Not quite. So what really is going on under the hood is we're designing a mixed state that realizes a transformation that is equivalent to this. And because a quantum mixed state, you can't distinguish between that mixed state versus if someone were to hand you like a pure state with some probability, it is robust against those error bars. So this is what we're going to aim to construct, and I'll show you how we do this and achieve this constant factor reduction in cost. So the key to doing this is to use something known as randomized compiling, which is a quantum computing tool. And what it says is as follows. In ordinary compilation, we imagine applying a unitary transformation of state on our quantum computer just deterministically. And in randomized compiling, we apply a unitary with some probability. So some unitary UI with probability pi. Okay? And this is equivalent to saying we're replacing a quantum channel, which takes our state rho and maps us to u rho u dagger, as this does, and replacing it with a quantum channel that is now a probabilistic mixture over a bunch of these unitary evolutions. So now the channel is just lambda of rho, that's the sum over the probabilities times ui rho and ui dagger. Okay? And rather remarkably, by doing this randomized approach, by randomizing over the unitaries we're applying, we can quadratically suppress the errors that we would suffer in approximating some target operation. So if we wanted to approximate some target operation with the deterministic method, suppose we do that and we suffer some error epsilon. Then if we do the same thing with this randomized operation, where we're now going to consider the error between our target operation and the quantum channel that we are constructing, that error can be suppressed to O of epsilon squared. So we could effectively go from like a 10% error to 1% error just by randomizing over the operations that we're applying. Okay. So this randomization might seem like kind of strange. It seems to almost come out of nowhere, but this is the intuition from where it comes from.
And how many copies are you taking the?
I haven't specified. It depends on what your operation is, but it can be as small as like 2. The set can be small or large. It depends on what you're trying to approximate. So intuitively, this is achieved as follows. If you were to imagine, say, n fixed errors that, say, your system is suffering, then these errors can add up linearly to some overall O of n error over, say, n iterations of whatever channel operation you're applying. However, if we consider n random errors, that is errors where the signs are now randomized, the overall error effectively performs a random walk. And as we know from StatMech, the standard deviation of a random walk is over square root of n, which is quadratically smaller than in the deterministic case. That corresponds to the quadratic suppression error that we realize with randomized compiling. Okay, so that is the name of the game. And you could imagine, what if we took this tool and applied it to polynomials? That is, we now randomize over a bunch of different polynomials, and in doing so, we quadratically suppress the error that we suffer in targeting some target function or evolution. And you might wonder, how does this affect the cost? And indeed, this has been answered by some classical polynomial theorems. And specifically, a classical theorem that says that a smooth function can always be approximated by a polynomial of degree that scales as log 1 over epsilon. So basically, it says that any smooth function can be very efficiently approximated by a polynomial. So something like a decaying exponential can be pretty efficiently approximated, such that if you want to achieve some error epsilon, it scales inversely logarithmically with that target error. And if you recall from what I showed many slides ago, this is indeed the case for time evolution and for thermal state preparation. It holds true in general. And so as a result, the cost of realizing quantum signal processing, which scales as the degree of your polynomial, also grows as log 1 over epsilon. So if you want to realize some smooth function of quantum signal processing, that cost will also grow similar to this. And so then if we go ahead and put 2 and 2 together, you imagine applying randomized compiling to quantum signal processing, you reduce the overall cost by a factor of 1/2. Where this cost reduction comes from the error suppression, that is going from epsilon over epsilon squared, in combination with the O log 1 over epsilon cost. So if you just imagine plugging that in, you can apply a factor of 2, and that's your overall cost reduction. What this looks like in practice is as follows. If we were going to run a quantum algorithm, what we're going to do is we're going to evolve under some operation many times, and then measure our state at the end of the day. And so in ordinary quantum signal processing, this polynomial will always be the same. And so the cost in any execution of this algorithm will scale as the degree of that polynomial. On the other hand, as we show in our work, we construct a random ensemble of polynomials and corresponding probabilities such that the degrees of these polynomials vary at every step. And we can show how to sample from this distribution efficiently to realize this reduction in cost. And as a result, the average degree, which dictates the overall, the important cost of your algorithm, will be d over 2. That's again owing to the fact that the cost scales as log 1 over epsilon, which we are quadratically suppressing, by randomizing over this set of polynomials. Does that intuitively make sense? Yeah.
So the error that you're reducing is the error of the polynomial approximation.
Correct.
You're saying randomized approximation will give you less error then.
Okay. Yeah, so you can think of it as like the error in approximating the time evolution rate. There'll be some error epsilon associated with that, and you can quadratically suppress that by randomizing over a bunch of approximations. Where these approximations and probabilities are carefully chosen to realize randomized compiling. Okay. So in our work, we show how to construct this random ensemble of polynomials for any target function. Again, I'm happy to go into the construction, but it's a bit lengthy. But we show you can realize this for any target function. And as a result, stochastic quantum signal processing accelerates a large class of quantum algorithms. And in our work, we show that we indeed achieve this cost reduction of 1/2 for things like Hamiltonian simulation and thermal state preparation. So this cost reduction is an asymptotic cost reduction. So as the degree increases, the cost reduction approaches this factor of 1/2. Whereas beforehand, it might be a bit different, but it's guaranteed to converge to 1/2 as the size of your polynomial or computation grows. So in the asymptotic. So with that said, what we've talked about today is how we can use polynomials to guide the development of quantum algorithms. And I showed you very elementary recipes for this that include, say, general algorithms, which are based on approximation theory, and parallel algorithms, which are based on polynomial factorization, as well as randomized algorithms, which are based on smooth function analysis. And in any event, what I find most fascinating about this is that it's guided between this, it's sort of based on this interplay between these historical classical ideas on polynomials and how they can approximate functions and how they can be factorized, as well as the intersection of that with modern concepts in quantum computing, like quantum signal processing itself. So there's a very nice interplay between the quantum classical ideas that can spawn new developments in quantum. And going forward, there's a lot of exciting directions, I think, to be developed in quantum signal processing for algorithms and applications. And in particular, the question that I want to pose that I'm pondering very often is, what other properties of polynomials can we use to develop new quantum algorithms? Like, we've studied polynomials for hundreds of years, and we have a lot of results on them. And I wonder how we can better use these to design quantum protocols and algorithms. So some that could be useful are some properties from functional analysis. If we have ways of bounding the derivatives of polynomials, RB feels that these could be used to develop some complexity theoretic bounds on some algorithms. And in addition, it might also be nice to use quantum signal processing to verify properties of random polynomials in random matrix theory, in studying the roots of random polynomials, their results on that, and also developing ways to verify the predictions of random matrices. It can also be done through the lens of quantum signal analysis. So in any event, I think it'd be really fun to keep unveiling all the possibilities that we can achieve in quantum algorithms through the lens of classical polynomial theory. With that said, thank you all.
Yeah, a lot of the structure when in mathematics you do when you actually do quantum mechanics, as you don't do it entirely naively. You have some guess as to what that operator will do. That's a reference idea, and you think about changes from that. And so you don't require your calculation or your approximation to do all the work. You're just interested in the changes from a reference. So can one set up the same kind of development for a polynomial approximation to that will change from a reference operator rather than trying to have to do all the work of the operator?
What do you mean by a reference operator?
So, for example, suppose going back to Brenda's questions, can you predict think about what the phase change would be in a way back? So you may have some problem where you can analytically know what that phase change would be, and your actual answer, which you don't know, is a perturbation on top of that. So is there a way of formulating it in terms of that perturbation operator? Something, but I guess I'm foreseeing something involving a Magnus expansion where you have an exponential of that sum of operators, which the pieces may not commute, and then you have to end up bringing in the commutators of the p and so forth. But I would think that developing approximations to the corrections would be more efficient than developing approximations from the ground up.
Yeah, that's a good point. Like if you want to, say you have some simple way of doing Hamiltonian simulation, but it's not all that accurate, and you only implement those correction operations on top of that. I think conceivably you could do something like this, like in Hamiltonian simulation. You could imagine doing like trotterization, and then on top of that, a quantum signal processing sequence to fix up the errors in that. That is, I imagine it's possible. I don't know what polynomial you would need to do that.
I'm just trying to think like what new would one do? So, typically what one does is basically subtract off from the Hamiltonian in different forms. So I think we're just thinking of like mean field paths, then you sample around the mean field paths, but usually you incorporate that back into Hamiltonian, which then goes into either the IHT. So I feel like you're just doing a different polynomial. And maybe we're just thinking of something else.
I guess I don't quite understand what exactly reference operator is. Are we considering like perturbations from?
There are different versions of this that come in different flavors, but one can think of perturbations from mean field theory, sort of the average version of the operator, and then you want to take perturbations away from it that actually end up being more accurate. But usually people just put that back into the Hamiltonian. I mean, I know there are other ways of doing it, but yeah.
In principle, if you could find some way to, again, blocking code that perturbation or change from the Hamiltonian from the end field, you could use that to construct a polynomial such that that polynomial applied to your mean field or reference operation would get you closer to your target operation. I don't know what polynomial that would be, but I think that's certainly possible.
So the practical, you're trying to do time evolution, quantum mechanical time evolution, and it's the breaking, imagining that you can do that by breaking your polynomial of the powers of the Hamiltonian is not very efficient for long times, right? And so if you had something to say, basically the problem is some very simple reference Hamiltonian for which I can do things analytically or very simply or very accurately, and then the hard part of the problem, which isn't that, but it's a fairly small part of the problem, and so that I don't have to use such a high degree polynomial to deal with the correction that I would for the entire Hamiltonian.
Yeah, right. That could be more efficient in some cases. Like where the polynomial needs to realize the correction one just for like a small degree versus you do some like trotterization, it's already easy to implement. So this could be some like hybrid like trotterization quantum signal processing simulation. That could be interesting to think about.
So thank you for a great talk. I'm from a completely different world. I'm a numerical analyst. So I really enjoy the approximation theory part. So in numerical mathematics, we're concerned with two things actually. In this area, that would be the accuracy of your approximation, but also the stability. And approximation problems are very, very unstable if you do high order polynomials, unless you do things very precisely, you know exactly what you're doing. So I'm thinking of maybe the textbook thing would be Lagrange interpolation. The tiniest change of the most beautiful underlying function f leads to your polynomials exploding all over the place, or if they do not explode all over the place, they're just so sensitive to perturbations, they are unusable in practice. So what would that correspond to in this setting?
Yeah,
Choosing such a numerically unstable approximation, would it correspond to constructing a quantum algorithm that is extremely sensitive to noise? Could it be translated like
that
this?
indeed would be the case. So,
Okay,
like I mentioned earlier, we can change these parameters to change the polynomial that we find.
Yeah.
So suppose we have some analytic construction for our polynomial that we want to realize. And we can find indeed the phases that will realize this. That can be done to the same level of accuracy as you can achieve like classically. So if you want to do, you can compute the phases to like machine precision, then you get out your polynomial also roughly to machine precision. The question is then in inputting that phase into a quantum computer. If those phases do deviate by a little bit, it can really change your polynomial. This is a problem that I think has been approached maybe like 1 or 2 papers. But it is certainly a concern if you were to realize this, like for a very large degree polynomial where like a small change could induce a big change in the polynomial. It's more of like an experimental question in the sense that we know exactly what we should implement. And the question is then, can we design qubits and gates with a small enough fidelity to realize that exact rotation to whatever level of tolerance we want? But of course, like with quantum error correction, we could imagine doing something like that.
Yeah.
So if we had a fault tolerant quantum computer, you could do this. But if we do suffer noise of say, like 10 to the -3 in the rotations that we can realize, then that will indeed propagate to the polynomial at the end of the day. So that is certainly the case.
thank you.
Yeah. But like I guess the silver lining is that the error that we do suffer in just realizing those phases is as good as we can get in numerical approximation theory.
Yeah.
Yes.
Maybe in a similar vein, I'm interested, like, you're factoring these polynomials, but like, if I need to know the roots of the polynomials to factor them, like the quintic, you can't solve it by radicals.
Mhm.
So like, how do you actually in practice, if you have like a messy polynomial where no roots are like radicals or anything nice, factor it and
Yeah.
like,
So we would do it numerically.
Okay.
Like we wouldn't expect to use like a cubic formula or a quadratic formula, but we can determine the roots numerically again to whatever machine precision we have on our computer. And so you can do this by invoking the companion matrix method. So this is just from Wikipedia. So if you have a polynomial here, you can construct this matrix here.
Sure.
And then the eigenvalues of this matrix are the roots of that polynomial. And if you know the roots, you can design an arbitrary factorization. But it will again be done to within whatever machine precision you have on your computer and how accurately you can diagonalize the matrix. But that could all be done numerically.
Right. So kind of related to these questions, if you're doing polynomial approximation as on a like this, these are all bounded, so you're on some bounded interval essentially, right? You're essentially looking at a pointwise convergence of the polynomial to some target, right? Or is that not how you would think about this?
I've never taken an analysis class.
Or maybe what I'm saying is that it's essentially you're thinking about some Taylor expansion, right, of this curve, right? So there are other ways you can approximate polynomials, right? Very famously, there's like uniform convergence, and you do like sines and cosines for Fourier analysis. So it kind of
between uniform and pointwise.
so for example, uniform meaning like if I do like a square wave, you have a singularity, and then if you do sines and cosines, you can approximate that thing even at the jump point, right?
Is uniform kind of like an average case?
Uniform is it's kind of like you have an average error over the whole interval, versus pointwise is like you pick a point where you have the error can be as small as you want, but then if you start talking about interpolation, the farther away you go from that target point, the worse potentially your errors can get. If you have some like deviations, like some noise in your experiment or whatever, then the errors can get really, really bad for example, higher order polynomials.
Yeah. So we are considering pointwise convergence, and the error that we're specifically focusing on is the maximum absolute value between our polynomial and our target function over the interval.
Uh-huh.
So there could be the case where like they're exactly equal at some point, and there's another point where they deviate by 5%.
Wait, you
And
just
that's
said
why-
max, you did max?
Max.
So it's the max of,
That's pretty, serious. I mean, for the Fourier thing, you got the ears on the end. They can
Oh,
go
so
to infinity.
with discontinuous functions, so there's a trick to getting around that. Do we have a marker here?
You just.
I could. Yeah, so if we're considering continuous well-behaved functions, we would just consider the maximum error that is suffered. However, if you look at a function that is discontinuous, like a step function, that is used for some kind of signal processing algorithm, but what we do in that case is realize that in most situations, we are focusing on values that are sufficiently far away from the discontinuity. And so we ignore a region around that discontinuity and then replace the step function with, say, an error function that is a smooth interpolation between these. And then the error function is smooth and can be approximated by all of them. So we just ignore some region delta near the discontinuity. And as a result, we'll find the degree of that polynomial approximation scales as 1 over delta. So we just like ignore the discontinuity and smooth over it. And this was done in practice.
And then educating the stupid person now. So uniform means max deviation.
more or less, yes, over the entire interval.
Thanks.
It's basically saying like we need to consider the max deviation away from the discontinuity. So where things are still well behaved.
And this is helpful.
Like, I'm saying illustrate it, like, if you have a step function like this, what we'll do is we replace it with an error function, smooth like this, over some range delta that we're just going to ignore. And consider, basically we'll say like, if our algorithm ends up sampling something here, that counts as an error. And we're going to bound the error at the end of the day. And then we approximate this by some polynomial. But crucially, outside of this delta region, it's a good approximation to the step function itself. So that's what, and then the degree scales is 1 over delta times log 1 over epsilon.
So in that picture, is there some kind of stitching between the avoided central region that you do, or is this all one polynomial?
This is all one polynomial.
Okay.
So we replace it with an error function, and the error function can be approximated as a polynomial.
Okay, I also have a question about the polynomial approximation, which is that all of these approximation theorems demand that we're on some like compact domain, right? But I guess I was thinking like you're trying to do like thermal evolution, and you just have some like Hamiltonian, like the space of Hermitian matrices in n by n complex Hermitian matrices is definitely not compact, right?
Mm-hmm.
So like how large of a space can you handle on like, I don't know, a modern quantum computer?
Yeah, by space, do you mean the number of qubits that it acts on?
No, I mean like
the
how big a
eigenvalues?
space of matrices can you
Say
reliably?
like an arbitrary n qubit matrix that you can encode in a unitary. So that could be like a wide variety of Hamiltonians. Right? Does that kind of make sense?
Yeah.
Like if you can realize, and I had it on the slide earlier, if you can realize the block encoding of that operator, you can apply QSP to it. And there's a lot of operators that you can realize that of. On the other hand, if you mean the range of eigenvalues,
Yeah.
you can consider replacing your target operator with that operator divided by, say, the maximum eigenvalue. So if you divide it by some constant, so now all the eigenvalues are going to be -1. And because most of the polynomial approximations we consider are over some bounded range, like -1 to 1, like for instance with Chebyshev polynomials, then you can just apply all that technology to this, say, rescaled operator, and still generate polynomial transformations of the target operator.
I have another question. So I mean, since you're talking about polynomial factorization, sorry if this is too mathematical, but it's essentially the Gauss theorem only works over like a complete field C, like in this case, the complex numbers. So what happens? So is there any physical meaning if you work on something that's not C, say like the reals, where you don't have full factorization? Is there any like meaning to like real roots versus complex roots, or I don't know, if you want to be even more fancy, if you restrict the field to something else?
So I mean, one thing you could say is if you do restrict to real polynomials, that is, you want to take a real polynomial and factor its other real polynomials.
Right.
That might at the end of the day correspond to a simpler implementation of quantum signal processing. But I will say that quantum signal processing can also realize complex polynomials.
Right.
And so restricting yourself to just real polynomials is kind of detrimental in that sense. Like you could take this big real polynomial and split up into both its like complex and real polynomials. And then it might be a case of realizing those will correspond to like a simpler construction of parallel QSP at the end of the day.
But there's no like obvious advantages, like the real roots are easier to implement as gates than the complex roots.
No, because
Yeah.
the polynomial will correspond to the phases,
Mhm.
right? And it's not really any more difficult or easy to realize like a rotation through like 10 degrees versus through 20 degrees.
Sure.
And so the reality or complexness of the factor polynomials that you want to realize will just correspond to the QSP phases that do achieve that polynomial.
Suppose, you know, you weren't thinking real versus complex. Suppose you want to take advantage of the fact that you're not going to be that far from a given subspace of your original Hilbert space. You know, so, but, you know, in real physical problems, you may be interested in a particular mode, particular eigenvalue of your problem. And maybe, you know, what the real problem does is mix in the first few states near it. And so, you know, you don't have to worry about the full Hilbert space to get a very accurate answer. So is it useful to, again, to think about a subspace? You know, let all the work being done in this representation in terms of, you know, polynomial operators as just moving you, you know, in a subspace, moving you near some target.
I mean, is what you're suggesting to use a state-specific polynomial?
Well, something, you know, something that will not to perturb you far from some target.
Right. If like you have some operator that's a projection, but you know, if you do this approximation, the approximation actually takes you out of that projective subspace,
Oh,
and
I see.
but you actually care about projecting down to some target, for example.
Yeah. In that case, you need to construct like a specialized polynomial that gets you close to your target while also remains in that state or in that space.
Yeah, but I think quite literally, you know, there are problems where you think of sort of raising and lowering operators that move you away from a particular state. Well, literally polynomials of those raising and lowering operators move you so many states away from your target state.
Mm-hmm.
So that's a lower order problem than getting necessarily to the original state.
Yeah. I mean, I think there are certainly ways in which you could construct a polynomial that takes this into account, but you need some knowledge of what the initial state that you're applying this to is. Like, for instance, if you know, this is the simplest example, but if you know, like, your input state exists, say, within this range of eigenvalues, like it has support on the eigenvectors, eigenvalues are in this range, then we don't need to care about what goes on over here. And so it's cheaper then to approximate whatever target transformation you want just in this range than in the entire range. And so by virtue of that, you could realize that with, say, a smaller degree polynomial and thus a cheaper quantum algorithm.
There's also things that has answered to your question, you know, it could be that's compact, that,
Yeah.
you know, small, whereas the full problem is not.
Yeah, exactly. Yeah. So you just want to, if you want to look over things over some subspace of your entire possible eigenspace, then that is simply to do so.
Maybe for later, but I keep tripping on the fact of we have techniques for doing that in the Hamiltonian itself as opposed to in the polynomial. And so, you know, when is the trade-off that you should just do it with the Hamiltonian as to the polynomial that you're approximating? So like we have very robust tricks for taking what we need out of the Hamiltonian. But that's not necessarily the full function that you're dealing with. Anyway, longer discussion.
Perfect. Yeah, we can talk after. But I think this depends a lot on like what your Hamiltonian is and what your initial state is. And there's also something that I haven't directly worked on, so I need to like see what's really going on with the hood, translate it to QSP itself.
Go ahead. Yeah.
So ask the real question. Excuse me?
This is the messy theorem for you, by the way.
Go, Chris, go with your question.
No, it has nothing to do with technical. I want to know, you know, now that you're a big bad doctor, what's next?
Oh, I mean, do you want to do this first and then? Okay, so this is the messy theorem. So this is why I didn't want to present it because it is kind of gross, but it's like effectively saying that if we want to compute a trace of a polynomial of a density matrix, so we want to estimate like the entanglement entropy of some state, what we can do is we can reduce the query depth by a factor of 2k. So rather than do this with a degree d polynomial, we can do it with a bunch of degree d over 2k polynomials. But crucially, in order to measure this observable, typically we need 1 over epsilon squared measurements. But here we increase the number of measurements by a factor that's polynomial in the degree d, but exponential in the number of systems that are parallelized. Where this precise polynomial, as well as the constant factor that O of k, it depends on the polynomial. So there is a cost associated with doing a bunch of these like splittings of your polynomial.
Right.
But at the end of the day, there can be cases in which K might be modest, like 3 or 4 systems, in which case it's actually better to shrink your circuit depth at the expense of running more executions of your circuit.
Yeah.
And then this is actually quite similar to something known as quantum circuit cutting. Anyone has seen this? Which is a way to simulate a large quantum circuit on a bunch of smaller quantum computers. So you're going to simulate a large circuit on, say, K quantum computers. You also pay cost that scales as 2 to the power of K. But crucially, at the end of the day, we avoid an exponential cost in the degree of the polynomial, which means that we can retain exponential speedups, even if we do pay like additional costs in the polynomial. That's polynomial in the degree of D itself.
So first, your real question, I think.
Okay, we'll let that one to the end. I was interested in how do we take this and apply it to study systems, running code in actual real quantum computers. And I was wondering, are there any, of course, you're able to generalize like the standard search and Hamilton simulation and factoring algorithms with this new kind of framework to think about things. But you also introduce a constraint with different gates and different things that you would like to see in your hardware that would play nicely with this framework. Are there any of the architectures that are currently available out there today that plays a little bit nicer with the things that you would like to see in the hardware that you run an algorithm like this? Or do you think in the future we will see such architectures that play very similar with nice? Well, this, for example, I think all-to-all entanglement is kind of like requirement for this QSP circuits to run. Can you talk a little bit about that?
Yeah. So I don't know of any current architectures that are built to realize quantum signal processing. However, I believe there's some work being done towards this direction, and specifically had some conversations with Yang-Shan Ding, who's a computer science professor at Yale. And an idea that he had is, what if one could design a quantum computer that has a specific like QSP unit, kind of similar to how we have like graphics processing units, that just does the quantum signal processing part and realizes algorithms. And so there is certainly some ideas being thrown around about how one could realize that, but I don't think anything's materialized just yet.
Interesting.
But you can talk with Yang-Shan about it more. He's great to talk about.
Could you tell a little bit about some experiments? Have you managed to run some simulations, for example, for small systems in this? Could you talk a little bit about that?
Simulations, yes. I did this with, well, actually, I didn't run. We had an undergraduate right at the time. A project I worked on with UN where we did look into some ways of realizing time evolution with quantum signal processing. We did run some simulations just on systems that can be classically simulated. There are a couple papers that actually do realize quantum signal processing on noisy quantum computers. I'm happy to point you to these, but they consider small Hamiltonians, and a few qubits, such that you can implement a block encoding of this, and thus execute the whole QSP algorithm. But I think it's one of those tools that's like very theoretically beautiful and has all these nice properties, but really needs some time to build up, the quantum computers, and then the quantum computers that can realize quantum signal processing before we reap all the benefits of it.
Thank you very much.
So now
Last
what's
question.
next?
I applied some postdocs, and I also got some independent funding through the Department of Energy. So I'll be nominally supported as like a computational scientist through the National Lab, but I'll be working out of Harvard and Yale for some time.
Okay, great.
Well,